My name is Rúnar. I want to be talking about functional programming. So I work at Verizon here in San Jose, and we do a lot of purely functional programming in Scala, and we're actually hiring. So if you're interested in working with purely functional Scala, then go to careers.verizon.com and check out what we're doing. A lot of our core services for in the team that I work on are written in purely functional Scala. So we have like a purely functional core that ultimately everything else will run on. Okay, so I also wrote a book called Functional Programming in Scala, and I encourage you to check that out. But I wanted to, so mostly I want to talk about this book, and sort of how it came to be and why, and give you sort of an overview of what it is and what it's about, and a couple of examples, code examples. All right, so let's get started. So why did we write this book? Well, so I was doing enterprise Java back in the day, and I've been doing that for about 10 years or so. And my code was never very good. Like I was a mediocre programmer at best. And I found that the kind of thing that I was doing, I was repeating a lot of mistakes over and over again. I found it very difficult to manage complexity, and this was sort of enterprise scale systems, and so a lot of moving parts, everything sort of talking to everything else, and we had lots of bugs, and we had regressions, and well, things were generally just not very pleasant. And so what I was looking for then was a better way of doing this, a way of getting sort of better guarantees that the code is going to be correct, that it's going to work when it goes to production, that I'm going to be able to think about it, when it gets really large and complex. And so in this search, I came across functional programming. I came across Haskell, and started sort of picking that up on the side. And I actually started importing the ideas from Haskell into Java. So I was actually doing purely functional Java for a little while. And there's a library called Functional Java you can check out that is still going today, where people are doing purely functional programming in Java. And then somebody pointed out to me that, if you're doing functional programming on the JVM, well, you should be using Scala. And so I picked that up and really never turned back. Actually moved to Boston. I lived in Austin before I moved to Boston, and started doing purely functional Scala with my co-author, Paul Cisano. And it turns out that Scala is actually a pretty capable functional programming language. And you can actually use it like purely functional. People say that it's sort of an object functional hybrid or whatever, but you can just ignore all of that and just use it as a purely functional language. So in Boston there was a functional programming group. A Scala programming group, very much like this one, where mainly people were using Scala as sort of a better Java. So Paul and I and a few others had come to Scala sort of from a functional programming background, was seeking a functional programming language on the JVM. And so there's this divide between like those people who are just using it as a better Java and the people who are using it as a functional programming language. And there was no sort of comprehensive tutorial on how to pick up functional programming using Scala. Like the common answer was like, well, just go learn Haskell, right? And then you can go and import those ideas into Scala. So what we did was decide to write this book, and actually it took us almost 4 years to do, and now it's done. So you can go get it. And yeah, so we wanted to make this a good place to get started with learning functional programming, not just in Scala, but in any language. Okay, so the premise for the book is that we can use Scala as a purely functional language. And so we throw out side effects and things like that. So everything is written using pure functions. So the book's actually organized into 4 parts. And mostly I want to talk about things from part 1 and part 4 today. But so the first part is just an intro to FP, like what is functional programming, like why do we do this, how does it work, that kind of thing. And then part 2 is a series of tutorials on designing functional libraries. So it gives you sort of a very in-depth look at the process of designing purely functional systems. And then in part 3, we start abstracting over this, and we start looking at patterns that come up over and over again when we're doing functional design. And that gets us to things like monoids and monads and functors, traversables and things like that. And then part 4 is sort of about the real world, right? So at the end of the day, our programs have to like actually do something. They have to like, manipulate some state, or they have to, make the computer do stuff. And so that's what part 4 is about. So so let's start with this from part 1 of the book. What is functional programming? So people have their own ideas about sort of what this means. And some people say, well, there is no definition of functional programming. It's whatever you want it to be. But in the book, we give a somewhat precise definition that we find actually useful. So functional programming, strictly speaking, is just programming with functions. More specifically, or if you will, it's programming with pure functions. But really, a function in a very strict sense is pure. That is, a function has a type a to b, so it takes a value of some type a, and it will give you a value of type b every time. Right? And if you give it the same value twice, it will give you the same answer twice. And it will do nothing other than return a value, and the value that you get is a function of the argument. So it always returns the same value given the same argument. This also means that a function doesn't have any dependencies on the overall program state. So whenever you call a function, you don't have to worry that something outside of it has changed, and so when you call it again, it's going to do something different. A pure function will always do the same thing. Right? When you call it with a given argument foo, it always, and the function is f, it will always return whatever f of foo is. Right? And will do nothing else. This also means that the result of calling a pure function, when you call a pure function and you look at what it gives you, you are looking at everything that the function did. That there is nothing else to be understood. The function didn't do anything. It just gave you a result. And that can be very powerful. So, sort of in summary, we're not allowed to use side effects. That is, the function isn't allowed to do anything sort of on the side. It's just allowed to calculate the answer. So that means that we don't use things like I/O directly in the implementation of a function. If we want to do I/O, we have to put that in the value of the caller. In the value that we give to the caller. Okay, so we have to somehow embed the fact that we want to do I/O in the result, because the only thing a function can do is to return a value. So we say, hey, caller, some I/O needs to happen here. So functions don't actually go and do I/O, but they return sort of a script to the caller that the caller can then give to the some I/O system at a convenient time to actually make the I/O thing happen. So
a question: are you going to have a Q&A part after you finish speaking?
Yes. I was hoping after we could have like an extended, or we could have like a discussion, like an informal back and forth. If that's okay. So we are allowed to use local effects. That is, as long as the implementation of our function, if it uses effects like mutation and things like that, as long as it doesn't escape the function, like for instance, if it allocates an array and then proceeds to mutate it and then throws the array away, that is not considered a side effect because nobody can actually see you doing that. So inside the implementation of a function, you can do all kinds of crazy stuff. You're just not allowed to violate referential transparency, which is sort of the technical core of functional programming. So we say that an expression E is referentially transparent if you have some program P, and then you take every occurrence of that expression in the program and you replace it with the evaluated result of that expression. That is, you give that expression to Scala, and Scala will evaluate that to a value, and if you can replace your expression with its value everywhere in the program, then that expression is referentially transparent. Things like 5 plus 2, you can always replace 5 plus 2 with 7, and it's the same program. And then we say that a function is pure if calling it with referentially transparent arguments is a referentially transparent expression. Okay? So that's sort of the narrowly technical definition. But what's the brass tacks here? Like, why would we do this? Well, the benefits of functional programming, I think, are broadly subdivided into these two categories, but they're really the two sides of the same coin. And so one of those sides is modularity, and the other one is compositionality. And these are hugely beneficial, I find, to my ability to reason about my programs. So modularity is the property that your software can be separated into parts, and those parts can be recombined and repurposed in ways that you did not necessarily anticipate when you created those parts. So sort of like components of some system, or Lego blocks or something. Like the designer of Lego blocks doesn't necessarily have anything particular in mind that you can build with those blocks. In practice, this means that modular software is reusable because, again, you can take any expression and sort of reuse it, right? If you have a pure function, then you can always reuse it wherever that's appropriate. They're also testable because pieces can be separated out and tested individually. They don't have hidden dependencies on overall program state and things like that. And they are parallelizable because the pieces can be separated out and run in parallel. So functions fit this description. Functions are modular because if you have a function from A to B, you have an A, you can just give it that A and you get a B, and this works every time. And you can always test of your function. It's always safe to call it. You just give it the A, the input value, and you look at the output value, and you see if the output value is what you expected. So that you don't have to set up any kind of test harnesses and initialization steps or anything like that. You just call the function. And it's always safe to call for multiple threads, and it never matters in the order in which you execute them on different threads, because they can never, your functions can't really talk to each other in that way. All right, so the other side of that coin is compositionality, and we say that compositionality is the property that your program can be understood as a whole, just by understanding the parts and the rules that govern the composition of those parts. Right, so if you understand the individual pieces, you understand the rules for combining those pieces, then you understand your whole system. And this means scalability because large programs are exactly like small programs. So programming in the small and programming in the large has the same character. Right? You're always just putting functions together. And any individual function could be implemented by a million lines of code, but at the sort of API level of functions, you don't actually care about that. And yeah, I would say they are reasonable. That is, they're composed of some parts that can be individually understood, and then there are going to be some laws of composition, and those laws ensure that as things get larger, they don't get more complex. They don't get more difficult to reason about. They're still just functions. And so they're reasonable because at every level, you have individually understandable pieces, and you can just look at the pieces and look at how they fit together, and then you understand your system. I know that's all sort of very high level and and vague, but bear with me. So, functions are compositional. That is, we can always take, if we have two functions and their types sort of line up, then we can always just put them together into a composite function. So if you have a function f from a to b, you have a function g from b to c, then you could just take the b that you got from f and give it to g, and then you have a composite function that you can just call. And it's always safe to do, and you can't really tell from the outside that it's a composite function. And the composite function isn't any more difficult to reason about than the components. So then, how do we do anything useful with pure functions, right? So if we can only just return values, how do we ever actually do anything, right? Are we just making our CPUs hot by passing values to functions? Like for instance, how do we do looping? If we don't have variable assignment. How do we do data that changes, right? We can't mutate. There's no global immutable state. How do we model data that changes? How do we handle errors, right? We can't throw exceptions because that's a side effect. And how do we do things like state and I/O? These are all very good questions. And the answers are basically that everything is a pure function that operates on immutable data. So with looping, we just do recursion, and Scala helps us do tail recursion, so we're not actually increasing our stack size as we do this. But yeah, so we just, whenever we want to make a function call itself, we just put the name of that function and it'll just loop. And instead of mutable data, we use immutable persistent data structures, things like list and option and things like that from the standard Scala library. For error hunting, we use things like option, either, or validation. That is, basically return values from functions rather than throwing errors. We reserve exceptions for truly exceptional conditions, things that no sane person would try to handle. And then the theme goes on with state and I/O, and they're also just data types. So if you want to do some stateful computation, you return a value to the caller that describes how that state is actually manipulated. And the same with I/O. You return a value to the caller that describes what you want to do. What I/O facilities do you need? And then there's some separate interpreter of that then makes those things actually happen. Okay, so let's take an example. Let's just look at an actual program, some code. So here we have a cafe, and it has a single method that allows you to buy a cup of coffee, and it requires a credit card, and it'll give you a cup of coffee. But what it'll actually do is go and actually charge your credit card, right? And so this has a side effect, and it's not really very testable because you wouldn't be able to just give any old credit card. It will actually go and charge that credit card. And it's also not reusable. For instance, if you wanted to buy 20 cups of coffee, you would have 20 charges to your card, which is probably not what you want. You want one charge of 20 cups. So a partial solution to this, if we try to address the testability issue, we can pass in sort of a mock system. Right? We've all done this, I'm sure, where you have, instead of your production payment system, you pass in like a test payment system, and then instead of actually going and charging the card, the test payment system will just make a record of the fact that this card needs to be charged, and then return the cup. So, and this is only a partial solution because this is still not reusable. Right? It'll still do multiple charges to the credit card. We call it multiple times, and it's also kind of side effect, like because you give this payment system and you expect that payment system to be mutated in some way, and then you go and look at it. It's very it feels kind of dirty, right? And so the functional solution to this is to have is to return a value to the caller. Right? So in this example, what I'm doing is, in addition to returning a cup of coffee, I'm also returning a charge. That is, I'm producing a description of what I actually want to have happen. So I'm producing a coffee and a charge to the credit card that was given. So a charge is just an immutable data type. It takes a credit card and it takes an amount. Right? So all this function does is turn credit cards into coffees and charges to those cards. So it's a pure function. And then somewhere else, there will be a charge processing system where we can pass all of our charges. We can batch them, we can combine them, we can do things like that. So there's a separation of concerns here. And this means that we can easily test this, right? So we don't need mock objects or anything like that. We can just write a pure function to test this thing. So we can just say that given a credit card, this is just a function that takes a credit card, and we need to say pass that credit card to buy coffee, and that will give us a coffee and a charge. And then we check that the price of the coffee matches the amount that was charged, and that the credit card matches the card that was charged, which is sort of the logic of the function. I mean, it's super simple logic, admittedly, but this same kind of thing holds for very large and complex things. And also, buy coffee is now reusable. So if we wanted to, if we called buy coffee 100 times, it would just give us 100 cups of coffee and 100 charges, and then we can go and coalesce those charges and charge them all at the same time if we wanted to. So the common theme of functional programming, I find, is that programming is not so much about writing programs as it is about writing programming languages. And so you make little languages for yourself, and they describe sort of exactly the kinds of things that you want to be able to do in any given function, and they can't do anything else. Okay? And then we have interpreters of those languages to sort of give them meaning. For example, in the previous example, was returning a charge, which is just a simple pair, right, of an amount and a card. But then we're imagining that somewhere else is a system that can receive charges and turn them into actual, actually send it to the credit card company and make it happen, or turn it into a test, right, to make sure that our program works in a user. So an example of this theme is in error handling in purely functional programming. So exceptions are side effects. Right? If we throw an exception, we are doing something other than just returning a value from the function. So instead of throwing exceptions in purely functional programming, we return a little program to the caller. And that little program tells the caller whether there was an exceptional condition. And that little programming language is called option. And so option has two instructions. It's a very, very small programming language. And it has only two instructions. It can be none, in which case there is no value, and there was an exceptional condition, or, basically we're saying this function doesn't have a value of type A, right? Or it can return sum of A, in which case we're saying there actually is a value of type A, and here it is, okay? And then the caller is actually responsible for interpreting what this means, right? If you want to throw an exception in the case of none, you can do that. If you want to do something else, you can then do that. So error handling is discussed in chapter 4 of the book, and so sort of skipping around in the book, but I thought this was a neat little example. So then the question comes up, like, if you start using option to handle errors or nulls or whatever, doesn't your code get polluted with options everywhere? Like, don't you have to make option the return type of everything? No, you do not, because you can always lift a function into the context of option. If you're not interested in the sort of optionness of your function return call, the return value of your function call, then you can always just take whatever function is interested in the value of type A. Here it's called f. So then you just take the your function and you map it over the option. And so you have an option A, and you can take any function of type A to B for any two types A and B, right? And that'll give you an option B that just transforms the value inside. So you're basically saying I want to ignore the noneness of the option. And the implementation of that is really simple. It's just saying, well, match on this option, and if it's none, just return it again. It's just none. But if it's some, then apply the function to the value inside and wrap it up again. Okay. So this is one way of handling the option. But the important thing is that the function f doesn't need to know anything about options. It doesn't have any options in its type. The other thing we can do with options is to extract the value inside. But in order to extract the value inside, we have to tell the option what we want to do in case that it's none, right? And so that's what get or else does. Get or else allows you to give sort of a default value in case that it's none. And then so you say, get or else z, where z is some value type A. I'm sorry, say z, where z is some value type A. And then if it's none, then it returns z. If it's some A, then it just returns that A, right? And so these are the two handlers, really, for option. You can either ignore the none or you can handle it. And then there's a composite handler called fold. So if you fold an option, you have to give it a handler for both cases. You have to say, well, if it's none, then you want to return this value type B. If it's some, then you want to apply this function of type A to B. And the overall thing gives you a B. So the implementation is that, if it's none, then it gives you the B. If it's some, then it's, if some of A, where A is the value inside. So this is an interpreter for option. Okay, so option is a programming language, and this is an interpreter for that language. Okay? So we can also compose options. That is, if we want to handle the sum case using a function that might itself have some exceptional condition, then we can compose those two things together. And we use flatmap to do that. So what flatmap does is that it takes the A that's inside. If there is an A inside, it applies F to that and returns the resulting value. Otherwise, it just returns none. And here I'm using the actual interpreter. I'm using fold to say, well, fold, and I'm saying if none, none, and if some, F. Okay? And this allows us to use for comprehensions to write imperative-looking programs. You might even say that these are imperative programs that work with functions that return options that may or may not fail, or whatever meaning you want to give to none, it may not be fail. Okay? So here, might fail and might also fail, might both fail, and so we compose them together this way. And the overall program here will return none if either one of those returns none. Otherwise, it will return might also fail. Right? So we can also use either, which is the same as option, except the failure case, which is conventionally the left case, it will carry some information about the error. So here we say that right of A is the success case, that's the actual value of type A, and then left of E is sort of the failure case, where E is the type that we want to ascribe to failures. And then we're going to have some interpreter for this language with two instructions, that handles both cases. So we have the ability to say, well, if it's left, then apply this function on the E. If it's right, then apply this function on the A. And the overall thing gives us a B, right, which could be anything. And on either, we have map and flatmap, and we can extract the left and extract the right with like default. We can say, here's a default error, give me the error if there is one, otherwise it's default. We can say, here's a default value, give me the value on the right if there is one, otherwise give me this default. And we can write all of those in terms of fold, and that's a fun exercise we want to write. So, theme is, we don't use exceptions, we don't throw exceptions, we return values to the caller. And those values are written in a small programming language that specifies exactly the instructions that describe sort of the semantics of failure. or rather, it's sort of the syntax of failure, and then you have an interpreter that gives us that syntax some semantics. Okay, so state is the same kind of thing. If we want to have, and this is where it gets hairy, okay? So if we want to have a computation that modifies some state, or carries some state through a program, right? Where each instruction in the program actually modifies the state, then we can do that purely functionally just by modeling the state transition as a function. If you're familiar with Mealy machines, then this is very much the same idea. So here, this is just a data type. It's a case class, and it contains it has a single member called run, and run is a function. And run takes a value of type s, which is the incoming state. That's the state before the action. And it returns a pair. And the s in that pair is the state after the action. That's the return state, the modified state. And a is some value that this action actually produces. That is not the state. So it's a stateful, it's a value of type A that transitions some state of type S. Okay? And here are two sort of primitive actions, get and put. And get actually just takes the state type S, and it returns that state, and doesn't modify it. So it puts S in both places. So it's actually state S of S. Right? So it actually gives you the value. I mean, it returns the value and doesn't modify it. And then put takes some new state and ignores the incoming state, the underscore there, returns unit, that is, it's void, it doesn't have any return value, but it's in the state portion of the return value, it returns the state it gave. So it sets the state. Okay? So before setting the state, we don't care what it was. After it is S, because we've set the state. And then get, before the state was S, and after it is still S. And we also return, the value that it returns is that S. Okay? It's a little bit, weird, but the value of this comes into play when we start composing these things together. So if we want to get and then put, or put and then get, or do some kind of composition on this. So then, the question arises, again, like with options, well, if we are doing this state thing, doesn't that mean that we now have to, whenever we call something that has that manipulates any kind of state, doesn't that pollute all of our text signatures now in state? Well, no, because we can lift. We can lift any function of any type A to B into a function that takes a state and returns a state. That is, if we have a state transition, so I guess it's a little bit confusing that state, uppercase state here, actually means state transition or state program, right? State manipulating program. So if we have some state manipulating program that returns an A, and then we have a function from A to B, we can turn our state manipulating program into a program that returns B, because all we have to do is to say, well, at the end of the program, apply this function to the value, right? And that's what this does. So this is saying there's some incoming, I don't know how to put a pointer on this. No. Anyway, so there's some incoming state S after the curly brace, and then we're actually calling run on this. So we're in some state action and we're running it, and that will give us a value of type A and a new state, right? The state after. And then the value we return from the new state action is f of A. So we apply A sort of at the end, f at the end of the program, and then we return the new state. Right? So it's the same state transition as run, except we apply f to the value. Okay? And we can extract the value from the state action. That is, we just run it. So given some value of type S, that is the initial state, we can run a state action given that state, and it will go and modify that state, and it will return a pair, right? It will return a state, a new state, and a value of type A. And so what we're going to do is ignore the final state and just return the value. So that allows us to extract the A from the state action. And we can compose these things, just like we did with options. So using flat map, we can use, we do composition, and this is just function composition here. So we have, our state SA, which has our run function in it, and then we want to produce a state SD, right? Given a function f that takes the value from the first state action and produces another state manipulating thing, action. So that is just, takes S1, which is the initial state, runs the first state action using that initial state. That gives us a new state, S2, and a value of type A. And then we call our function f on the value we got, and that gives us a state action. We run that with the new state, and that gives us a third state, which I'm not mentioning here because that's just the return flag. Anyway, what all of this does is allow us to use composition in for comprehension. So we can write imperative programs that are purely functional, that modify some state, right? And the passing of the state from one function to another is literally happening between the lines here. So here I have this function called modify, and it takes a function from S to S. That is, it says modify the state using this function. Okay. And so all it does is first it gets the state and stores that as S, and then next it puts f of S, which is the modified state. And this just desugares the calls to flat map and map. Okay, so this kind of composition is doing all of this state transition stuff for us. So that's sort of the trick for doing purely functional state. But the important thing to remember is that the value that's returned by this modify thing is just a function. It's a function that takes a state, returns a new state, and the value of type unit in this case. And then I/O. Now I'm jumping. Is there a question?
Yeah.
Yeah.
Excuse me. Is f pure in that case? Last line.
Here?
Mm-hmm.
Yes. Yeah. F is a pure function from S to S. So, for example, let's say you're counting something, right? And you want to say modify, and you want to say +1, for instance, as the function f. So it takes the int and it says that int +1, right? And then the overall function then will take the incoming state, add 1 to it, and that will then be the new state. And then if you called modify twice in a for comprehension like this, it would increment the state twice. Yeah?
On this one. So the put method returns a unit, correct?
The type of put, it takes.
The state.
What's that?
It's return a state or return a unit.
It returns a state of S in unit.
So the middle bracket will actually return the final state where the put operates.
Yes. Yeah. So what this actually detriggers to is like get and then flat map S and then put f of S map and then unit whatever. But the types of the line of the right hand sides of the arrows, right, in the for comprehension have to be of the same type as the overall thing, right? So we can go back to put. So you can see the type of put, the signature of put, is that it takes a new state and it returns a state action that sets the state. And then when we use that in the for comprehension, it's just function composition. Okay, so I/O, same principle applies to doing I/O. All right, so here, this is one way that you could model I/O in a really functional programming language. And this is sort of the kind of thing that we actually do in practice. What we actually do in practice is slightly more complicated than this, but the idea is the same. So we just have some purely functional data type called I/O. And it has a number of cases. And the cases are the actual instructions that you allow in your program, in your I/O program. And in practice, you can compose these things together and things like that. So you can have programs that can read from the console, and then you have programs that can like look at the clock or talk to the network and things like that, and then you can compose these instruction sets together. But here I'm just doing a very simple console thing. So you can embed a value of type A in an I/O program with const. So const just takes an A and it gives you an I/O program, and the semantics of that are not specified, but the idea is that this is a program that returns that A. And then there's an instruction called readline, which is an I/O string. And the idea there is that that instruction will read a line from the console and give you a string. And then there's a write line, which it takes a string, and the idea there is that it will actually write a string to the console. So it's an I/O unit. It doesn't have anything to return. And then we have this compose, which looks conspicuously like flat map. It takes one I/O action, and it takes a handler for, for appending another program onto it. So you have an I/O of A, and you have a function that can receive the result of that I/O program and produce a further program. So sort of a continuation, right? So some program, and then there's another program that receives the output of it that's appended to the end of that program. And so we can write little I/O programs sort of totally vacuously in this little language, right? This doesn't really mean anything as of yet. It's just sort of a syntax tree. So we can say, well, read then write, which is a little program that reads a line and then prints that same line to the console. Right? So all it does is just like read a line from the keyboard, print it out back out to the console. But obviously this is just a pure value. Right? It doesn't actually do anything, but it describes something. And so we can have an interpreter for this. So the program argument here is a pure value. It's a referentially transparent expression. But run here has a side effect. Run is not part of our program. So run is sort of shell outside of our program, and our program is here sort of, you can think of it as making calls out to the shell. And the way it does that is just by returning pure values. So we have some program that's written in this I/O language, which is, if you recall, just either a const or a read line or a write line or composed of any of those things, or composed of composed of composed. So it's sort of a list of instructions, and then this run thing will recurse over this list, and it'll say, well, if it's a read line, then just read a line from the console. So this is Scala's read line here. And if it's a write line, just print that to the console. If it's a const value, then we just return that value. But if it's a compose, then run both of those things. Okay? So it's recursive. This is not tail recursive, but we can make it tail recursive, but that's more complicated. But here's the thing. We don't have to do any actual I/O. We can model I/O as a totally pure thing if we want. Let's say we want to write some tests of a console program, and we want to make sure that given some inputs, it will give us certain outputs. Right? That's actually like a really difficult thing to do if you use the actual console. It's like, how do you inspect what Java or the JVM has written out to the console? I mean, you can probably do it. It's like going to be really complicated. But if you use purely functional programming, you separate that concern out. And so here we have our program of type IOA, and we will take two lists, and one of those lists will be the input buffer, and the other list will be the output buffer. Okay? And the return value overall of this thing is an A, and the two lists, the output and the input, the new input buffer and the new output buffer. So we could model this as state, right? So it's a function from a state to a new state, and that also returns some A. So we could write this as a state action. So the idea here is that if we see a read line, we just get the head of the input buffer, and then we take the tail of the input buffer, which will now be our new input buffer, okay? And we leave the output buffer unmolested. And then if we have a write line, then we have some x that we want to actually write. And so we put that on the front of the output buffer. And we leave our input buffer intact. And the return value is going to be unit. And if we have a const, then we simply return that and leave both buffers intact. And then if we have a compose, then we run both of those things in recursion. Right? Totally awesome. So, functional programming is really about, I'm sorry.
Before that, if we go back to that slide. So, this is
This one?
yeah. So, this is a pretty beautiful interpretation of the appropriate stuff in Haskell. But I don't see where can we see that I/O is a monad, or is it a monad here at all?
This sort of is a monad. So if you know the requirements for being a monad, and that's in part 3 of the book. So the requirements for being a monad is that you need to have a unit, that you need to be able to embed values in the monad, and that's what const is here. You can take any value and you can put it in this I/O thing. The other requirement is that you need to be able to compose programs, and that is composed here. So you need flat map and unit, and compose here takes. You could implement a flat map method on I/O that just calls compose. It wouldn't be totally correct because you could have a lopsided. A left-leaning compose is not going to be the same as a right-leaning compose, things like that. But that's beside the point here. What's that?
We lose associativity?
Yeah, we lose associativity with this particular formulation. So, yeah, so functional programming is all about separating concerns. Right, so, and it's a very deep separation of concerns. Right? It's not, I mean, programming in general is largely about separating concerns and figuring out how to subdivide a problem. But functional programming takes us as far as you can possibly take. You work with little languages that do exactly what you want and nothing more. And it separates the what to do, like the syntax of the thing, from how to do it, the actual semantics of the thing. Right? So there's always we strive for this separation of those concerns. So yeah, instead of actually going and doing those side effects, we always have pure functions, and those pure functions return pure programs, and those programs describe the effects. And then there's going to be an interpreter for that program that actually executes those effects and gives them some meaning. Okay, and so now I want to just open it up to discussion about this. Like if you have questions or concerns or thoughts. Yes, sir.
Well, are we supposed to speak into the microphone? I think so.
Oh yeah, I think so. It's probably better. I can repeat what you say.
Okay, yeah, that would be better. So it's not so much of a Scala question, just generally about functional programming. I personally really am on board with functional programming and want to do it at any and every opportunity. But I just wonder if it's only realistic at an application level, whereas at a systems level maybe less so. For example, suppose you had to write the Linux kernel, or the majority of the Linux kernel, using either a functional language or functional constructs / paradigms. Is that realistic in practice? And if so, do you ever see somebody writing the majority of an operating system kernel in functional language?
Yeah. Okay. So the question is whether you're saying that the functional programming, you can see the value at the application level, but at the sort of systems level, and especially like the embedded systems level, and like kernels and operating systems and things like that, you don't see the value as much. Well, I actually think that the value is sort of amplified at those system boundaries, because I mean, yeah, obviously it might be difficult to like rewrite the Linux kernel in a purely functional way. So you may not have to, right? It may be that the requirements that you have for a system kernel is a lot smaller than Linux. And then if you do this using purely functional programming, and especially with strongly typed purely functional programming, you'll be able to reason a lot better about sort of the boundaries and about like safety and things like that. And also, pure functions are compositional. So you may be able to start very small with sort of the exact kernel that you need, and then you'll be able to compose that with a larger system that maybe somebody else wrote.
That would be great if it reaches that stage one day.
Yeah, I mean, I don't think we're there yet, obviously, but Nix OS, yeah, okay. Operating system written in Haskell. There you go. So, yeah, there are lots of very small operating systems as well, that tiny like microkernels and things that are written in pure functional languages. Can't think of any off the top of my head. Nix OS. Alright. Yeah.
So you use the word interpreter several times in your talk.
Yeah.
So I suppose there are some interpreters that come with Scala for I/O and state. I suppose I'm not a Scala programmer, but perhaps it comes with. When I get my little language, am I going to how do I ensure that my interpreter is efficient and it's not
Right. So the question is, how do you ensure that your interpreter is efficient? And you mentioned that there may be some, there's code that ships with the language that people have hardened and tested, and people have made sure is very fast. But yeah, I guess it's the same answer with how you make sure anything is efficient. Right? It's just whenever you write software, you have to make sure that it's efficient. You may start out with something that's inefficient, and then iterate towards something that is more efficient. But yeah, generally, I mean, all of this stuff, like interpreting and things like that, have a constant overhead. There's a garbage overhead and things like that. But I think that at least for me, most of the time, I want to do the correct thing first. Like I want my concerns separated as much as I can before I then start thinking about how to optimize that and perhaps combining things again. Like it may be the case that if you want to assemble a jet engine out of components, it may not be very performant, right? But building it as a single, as a single element that you tested as a unit, that may be a better choice. So I think it's the same in software. Yeah.
But how efficient was that thing that you wrote there?
How efficient is it?
Yeah, how efficient was it? I mean, what's the performance for that?
I don't know. I mean, it's linear.
You wrote it.
It's linear in the size of the program. So.
But is it even measurable?
Is it measurable?
Right.
I think so. Yeah. It's just. I mean, you can. Actually, I mean, I think this particular thing here is probably quadratic in the size of the program because of the compose. You might have very deep compositions, and you may need to go all the way to the bottom in order to be able to go back to the next instruction. So this particular thing is probably quadratic, but in general, you can write this in time that's linear in the size of the program.
But is this reasonable in the real world, or this is?
We use this at Verizon. We use this kind of thing a lot in the real world, in core services that are pretty fast. So, and we measure how fast they are. They measure pretty well. But this little toy program, I haven't obviously measured, but I imagine it's quadratic. Yes.
So is the difference between this compose and a flat map only a signature difference?
Yeah, I mean, you can imagine writing flat map that's just implemented by compose, right? So this compose class here is it's just a data type, right? So it's kind of totally vacuous, right? You just say compose, and you give it the A, and you give it a function, and it's just a tag in memory, right? It's just an object that contains those two things. Right?
So I have a follow-up question.
Yeah.
So how frequently do you run into cases where you're using a for comprehension and you're dealing with one type of monad, and you end
sorry, I'm not repeating the questions for the
So how frequently do you come across cases where you write a for comprehension and you start off with, say, working on validation or something like that, and then you call something else with either or Scala try, and you have to convert from one type to the other?
Oh, right. So your question is sort of mixing and matching monads.
Is
right?
there a good, good thing like for which will let you deal with that?
Yeah. So this is sort of it's a very general question, and the question in general is how do you compose monads together?
Different types.
Different monads together, right? And so one answer is monad transformers. So where you will have, instead of having like I/O here, you will have, well actually I/O is not a good example, but let's say state. So instead of having state, you will have a state T that takes as a type argument some other monad that it then composes with and flat match over as part of its own implementation of flat match.
So the solution is to write a monad transformer which deals with both kinds of monads.
That's one solution. Another solution is to use monad coproducts, which I gave a talk on at Scala Days in Berlin last summer, and that talk should be available online.
And dig it up.
Yeah, the monad coproducts should come right up.
Thank you.
Yeah. So that's sort of the thing where you have, like, instead of having just a list of instructions like this, you have lots of lists of instructions, and you can compose them together. You can say, I want an I/O program to have like this, like I want my instruction set to be one of this or this or this or this, right? And so then you can compose them together and mix and match. So you can say like, well, I want a TTL thing here, and I want the network thing, and I also want system time or a random function, stuff like that. So, yeah.
Can you use your book as a first Scala book, or does it require prior experience?
Oh, can you use the book as a first Scala book, or does it require prior experience? I think that really depends on. I know people that have used it as a first Scala book and found it helpful. I mean, good as a first Scala book. But I think it depends on where you're coming from. Like if you're coming from Java, for instance, then yeah, I think you already know most of the stuff that you need to know in order to use the book as a first Scala book. If you're coming from nothing, like if it's your first programming book, that I don't think that's a good choice. I think you should definitely go with it. Yep.
So, what's your advice if you have a mixed programming in your system already? Like you're part of Java, part of Scala. How to transition your existing code base gradually to functional programming?
Oh, right. So how do you transition your code base gradually to functional programming? That's actually a really interesting and difficult question. So when I was first starting with functional programming, I was doing purely functional programming in Java, and it was kind of a slow transition. So what we ended up doing was zeroing in on sort of core components or things that are sort of very, very well contained, and then converting those, and then calling from other things into them, right? So I think the general answer is that you want to do it from the inside out, right? So transition your core components and things that are sort of at the center of your software stack, your functional things, and then gradually, like do different components, and then maybe gradually move out to sort of the glue that glues those components together, and then eventually you'll have like a shell on the outside, your peripheral services that are using these purely functional ones. I think that's sort of the general answer. Yeah, one over there.
What you described sounds good and interesting if you play in your own sandbox, right? Like when you go at Java level, there are something like exceptions, like other libraries you may want to use, right? But can you talk a little bit on how you kind of put things in to functional code? Because if you have just your own code and you write it either from the beginning, that's fine, but then you put just some other functions or exceptions.
Yeah, so the question is about calling other people's code, calling in, side effecting code from purely functional code, right? Don't do that. So what you want to do is you want to make an adapter, right? You want a thing that calls both of them rather than like, you never want to call an impure program from your pure program, because obviously then it's no longer pure, right? Now it has a side effect.
Because you're not allowed by compiler to actually write case.
Right, yeah, well, that depends on your language. I mean, Scala will happily allow you to, Scala does not enforce purity at all. So you're actually totally on your own with regard to that. But, yeah, so I think, so this general approach of using these little languages, I think, lends itself very well to adapting to other, outside code, right? Because then you model the language that you want to work in, and then you have an interpreter that turns that into the language that somebody else sort of imposed on you, right? So you have some, let's say you have some Java library that you don't like very much, or it's it's full of side effects and it does all kinds of nasty things, global mutable state or whatever. What you want to do is just model the things that you want to do as a pure data type. Have an interpreter then that interprets that data type into calls to that sort of at the edge of the world, right? Does that make sense?
So what you're saying, you need to extract all of the semantics from that impure code and put it into the interpreter?
That is, yeah, so extract the semantics from the impure thing and put it in the interpreter, yes.
That's a doable thing?
I think that's a doable thing, yeah. So recently, so this weekend actually, a library that I worked on called Stoop was called into not MongoDB, CouchDB. So it's a CouchDB client for Scala, and it's a purely functional client, but it just it's a thing like this. It's a list of instructions basically of all the things that I might want to do to a couch database: create documents, get a document. Those sort of the primitives of my language. And then I used, some other API that actually goes and talks to CouchDB, an API that I don't want to use, right? So I make the API that I want to use, and then I have an interpreter into the API that I don't want to use. And I think that's generally true for like everything, for all software that you write, right? There's some low-level API that you don't want to use, so you write a high-level API that you do want to use, and you translate from one to the other. That's just like everything works that way.
Right, but in Java you don't have this layering of exceptions, for example, and actually you can catch things at high level, but here you cannot afford to let exceptions for nobody.
Right, yeah. So if things are throwing exceptions and things like that, you want to not call those things except from your interpreters. Interpreters that are called at sort of the edge of the world. Yeah.
But then you lose the context, right?
Then you lose the context?
Because an interpreter, you don't know where in that original program you are.
I'm not sure I understand what you're saying. That you lose context.
So say you
If you have
compose.
multiple layers, then like everybody use and you can make different.
If you have multiple layers. Oh, you mean if you are calling your interpreter from a pure program again? Okay.
Even simpler, like you compose two writes, and each write could fail.
Yeah, that's true.
In that interpreter, how do you know which write failed?
Right. So okay. So you're composing your program, or you have two writes, and one of them might fail. And how do you know which one will fail? Right. You can get as clever about that as you want, because this is your programming language, right? So you could explicitly model failure here. You could have one more case that says fail with an error, and then you have no information about the error other than like failed, or there might be a string or something. Another thing you could do is in your interpreter you could actually return the failure together with the rest of the program. So you just say, I encountered an error, and here's the remainder of the program that I wasn't able to run, right? And so you can actually just then inspect and look at the program and say, okay, what's the next thing that it would have done? Right? And you can then recover from the error and then resume it. There are all kinds of things like that. And that's, in fact, we do that in Stoop. if the HTTP connection is fluctuating or if the server is down or something, we retry on schedule, and the interpreter actually suspends the program because the program is a list, right? So it just returns the remainder of the list and waits for 5 minutes. And like, okay, let's resume the program. Right? It's super easy because it's all just data. It works out really nicely, and it's not that slow. So, yeah.
So on a more practical front, once you have pure code and you have new developers coming in, how do you maintain that? Do you have any tools that make sure that nobody puts their logs to you or something leaves?
Okay, so with regard to large teams and things like that, if you have, like how do you enforce the discipline of purely functional programming in a team? Right?
Yeah.
That's a really good question, and so what we do at Verizon is that we have a sort of a core architecture team, and it's sort of our job to police this, at least sort of in the core services. But what people do at sort of the periphery is largely up to them. So the individual leaders of the individual teams, they will do whatever they want. But we try to make sure that at least the core services remain purely functional. So we keep a tight control. The closer we get to the center of the system, the tighter our control. And it has to be ultimately in Scala. It has to be a manual control. Right? It's a code review thing, basically.
Yeah. I was hoping there was a magic switch in the compiler or the IDE somewhere that day.
There is no magic switch. Like you can throw exceptions and you use nulls everywhere, whatever. It's largely I mean it's a culture of purely functional programming that you have to just kind of grow in your organization. And what we do is actually, this is kind of relevant. I mean, we might have advocates on some teams. There's a person that is well versed in purely functional programming and will then teach the others and sort of, gently help them to come towards this thing. Yeah.
Hi. So I have a question. So when I was thinking about your example about using credit card to buy coffee,
yeah.
And you said that pure functional programming should not contain state. So it means that it won't check whether the credit card would exceed the credit limit already, and it will call this function numerous times. And I think in the real world we have to update a database at some point. We have to change the state at some point, but according to the functional programming paradigm, it seems that we have no way to do it. So I
yeah,
find
no,
it
of course we do. I mean, ultimately, at the end of the day, there's going to be something that actually handles these charges and actually goes and talks to a database and makes it actually happen.
And there will still be state for that, right?
Oh yes, absolutely. I mean, there will be, you're going to be actually contacting the credit card company. There's going to be, a TCP connection. There's going to be, fax machines are going to be calling each other. There's all kinds of stuff that's going to happen, right? And that's all going to be controlled by some program that is not your program, right? Because your program is not about fax machines and calling credit card companies. Your program is about buying coffee, right? So all of that logic that has to do with credit cards doesn't belong in your program. This is a separation of concerns. And you talk about the ability to check if the card was denied, right? So you could model that explicitly here. You could have two handlers, right? Just like in the either example. So you could say it's either going to be a success or it's going to be a failure of some type, right? And then you can inspect what that type was, and that failure could, for instance, be, well, the credit card was denied. Right? So that's then going to be a data value that's explicitly modeled in your program. Does that make sense?
I still think that, well, yeah, it means that we can do our program like in functional program.
Yeah.
But there has to be a dirty word that they have to handle
There is
something outside functional program.
Right, yeah. Obviously, at the end of the day, there's somebody is going to then take the thing that you produce and is going to actually run it on a real system and like make stuff happen. Right? That's absolutely.
Okay,
We don't want to just like make our CPUs for them. That's not what we're doing. Yeah. One over here.
I have a question. You mentioned that strong tabbing helps pure functional programming, which got me thinking. I didn't even think that you can do pure functional programming without strong tabbing, but apparently you probably can. So can you talk about the connection between pure functional programming and type systems? So it's there and not exactly one and the same.
Right. So is there a connection between purely functional programming and type systems? I think that's sort of a deep topic, and probably is a topic for like a whole talk, or even a series of talks. But yeah, I think you can certainly, just like you can do purely functional programming in Scala without any kind of checking of whether you're using side effects. You can also do purely functional programming in untyped languages without any kind of static checking of whether you're actually manipulating your values in ways that is allowed. But I think that at least for me, I want to get as much checking as I can, and if I can get it for free, all the better. If I have type inference and things like that, I definitely want that. But sort of the ultimate functional programming is, so there's a real connection between side effects and exceptions and like programs crashing and types, right? So a program is essentially I can talk about this forever, but so there's something called total functional programming, okay? And total functional programming does not allow you to write it. So the types will then be so tight that you're not able to write any programs that crash or hang or throw exceptions or have any side effects. All programs have to terminate, right? And so I really think that this is sort of a continuum, right? And so dynamic or untyped programming in languages like Lisp is sort of at the other end of the spectrum where you have no guarantees of that at all. Yeah, no, I really do think that's very tightly connected.
I think it's kind of confusing when you use pure, because in this case generally it's like pure, like you're not really when you run on top of a vanilla interpreter like Java doesn't have or like semantics or generally like pretty pure for that, right? Because pure functional for that. You're doing the backend that's pure.
Wait, so you're saying it's not really pure programming? It was fake pure functional programming?
I didn't want to use fake, but stronger word, but maybe like I don't know, simulated.
Well, I think it really just depends on what you mean by pure. I mean, what I mean by pure is that a function call is going to be a referentially transparent expression, and then there are some nuances that you can sort of introduce into that notion. Like you can say, well, all Scala programs have a side effect because object
something.
What?
Because they do something eventually.
No, because object equality is a side effect. Right? You can always, if you call a function twice, you might get the same values that are equal, but they're not going to be the same object. They're not going to be the same instance on the heap. And you can actually inspect this in Scala. So you could say that with regard to object equality, and we actually talked about this in chapter 14, I think, of the book. And so we can say that object equality actually destroys purely functional programming, just the fact that you can do it. But you can just program in a subset of Scala that does not have object equality. But that requires a discipline. It requires the same discipline as doing purely functional programming in Scala in general, right? Does that make sense? Yeah. And there's a really good paper called Fast and Loose Reasoning is Morally Correct, which talks about this relationship between total functional programming and there's a connection with the types. And so that you can always reason in a subset of the language that you're in, and even though that language may include, instructions that have side effects and may crash programs and things like that. Programs that would be correct in a total language are still correct in the non-total language, or at least the statement is that if two programs are the same in the total language, then they have related semantics in the non-total language. And so it gives you sort of a relation that you can reason about. It's a good paper. It's great. Fast and Loose Reasoning is Morally Correct. It's pretty mathy, but it's pretty great. Yeah.
So is there a way to statically check whether a function is pure then?
Is there a way to statically check whether a function is pure? In Scala, you cannot.
Scala.
No.
Unless you're a compiler.
If you are the compiler, yeah, you can. I guess you could try to write a compiler plugin or a totality checker for Scala, but you would have to disallow a whole bunch of stuff and I really don't know if you can, but it might be fun to try.
The same question in Haskell. Can you do that in Haskell?
In Haskell, every function is pure. The side effects are not allowed. So there are certain, GSC allows you to do like unsafe perform IO and casting and things like that. And of course, there are compiler bugs and things that you might be able to exploit to actually do unsafe casts and things. But no, Haskell is a purely functional programming language and it does not allow side effects. And yet, people write operating systems.
So it accepts for exceptions, right? Like if you take a list and take it, it's not a total function, right?
Right, so totality is not, right, so in Haskell, with totality, you're on your own, right? Proving that programs terminate is not a part of Haskell's type system. There are other type systems that prove that for you. Anyway, I should...
Can we come back to that side effects and credit cards and Mongo wrappers? So you can't really have pure functional program anyway, right? Because even your wrapper around Mongo will break the purity.
You don't...
Because you cannot call it twice and get the same effect. It's going to write to the database or commit credit card transaction.
Well, that's the thing. You don't write a wrapper around it, right? You write...
Can you elaborate on that?
So it's just like this, right? It's just like with the credit card, right? So you return, and you don't wrap a call to Mongo, right?
Return a script that the function that does the call.
No, you return a script that describes the call, and then there's a separate interpreter of that script that then actually performs the call. If your program is pure, the interpreter may not be pure. Does that make sense?
But the interpreter is still part of your program.
The interpreter is not part of your program. The interpreter takes your program as an argument. Right? Makes sense?
That's part of your executable.
Yeah, it's part of your
It's part of
executable.
your
It's part of your
process.
overall environment.
But
Yeah.
not the source code.
Right. So yeah, it's you can write your logic, your core logic is purely functional, and that it's important to remember like what that means. It means that it's compositional and it's modular, right? So hold on to that because it's just purely functional because I want it to be pure. That's not really the point. The point is that you can reuse it. It's testable. It's clean.
So when you are saying separating concerns, what are exactly concerns there are? What do you mean by it?
what are the concerns that are being separated? So broadly speaking, the concerns that are being separated are what to do and how to do it. Right? So here, for example, in the charge thing, what we want to do is to charge a credit card. How to actually do that is defined somewhere else. Yeah? Does that make sense?
So can that explanation apply to separate your program from others' program? So your program is hardware? I mean,
yeah, okay, so the question is, does that same principle apply to separating your program from other programs? I think so. I mean, I think if you, in very sort of broad, in broad strokes, like every program is like either a compiler or an interpreter of something, right? And so you write programs that then, you know, produce inputs to other programs, or you write, and when I say program, I mean very generally, like, you know, functions, methods, any piece of code is a program in that sense. But yeah, I think that principle probably applies very generally. So, with 4 people here.
My kind of question is, functional programming has been there for a long time, so why is it coming back? Why is it important now? Why wasn't it a big deal than 15 years ago?
I don't know the answer to that. I really don't.
Commodity hardware.
Commodity hardware?
Yeah, I think so.
Yeah. Processors are not getting faster.
Garbage collection? Right. Yeah, no.
Sort of like asking why a specific song got popular. You can just sociological thing possible. We just something caught on.
No, I think it's, yeah, the technology is probably just starting to be there.
If we use the song analogy, it might become more popular next week. We want to learn functional programming.
Right? I mean,
well, hopefully it's not, right?
It's easier to do multi-core
there's a lot of things like you can give a lot of value for that then don't catch on. I think the one like that caught on because that didn't because it did. Sort of like I think Ruby caught on because Rails was popular.
But it's not the same thing. Like behind functional programming is math, right? And you have all of this foundation, right? So I think it's not learning is better because in case it's difficult to map correctly that math functionality to the compilers, right? So we can only take it so far, right? Haskell is taking that, Java is trying to take it and do that, and Scala, we're doing that.
So you're saying we can approach sort of asymptotically
But even
the end goal.
JavaScript is having functional libraries nowadays, right?
Yeah, lots of languages are now functional programming libraries, and yeah, people do monads in JavaScript.
But the strict is coming from the functional mathematical apparatus, so that's the possibility and the intention about there, that's the pure math, right? So that's just kind of
Yeah, that's something that we should, I think bears emphasizing is that what you say, the fact that a lot of functional programming concepts actually come from mathematics and are informed by mathematics, and this actually gives us something very important. It gives us, you know, 3,000 years of human knowledge that we can now apply to our software construction. So I think it's hugely important, and just simple things like conceptual integration, like the fact that, you know, there are lots of different ways that you can construct a program, but there's a certain pattern that we then can given, like for instance, monad, right? Monad is mathematical concepts, but we can see this, you know, when it occurs, and we can say, okay, this is a monad, and this allows us to integrate all other things, right, that are monads, and we can then talk about monads in our programs. We can say, okay, well, this thing takes a monad as an argument, and it does something with it, right? So I think that's hugely important.
functional methodology what we address now fits when we use the word monad. I think we should talk about functional programming without using monad.
I agree that you can do a lot of functional programming without monads, but monads afford you a certain kind of composition that is very, very important.
It's like talking about Java without using design code.
Is my
Could you give an example of where you try to model a problem with, say, state, and probably it turned out to be better using I/O versus state?
Is your question using I/O versus state?
Yeah. So how do you know you got it right?
Oh, I will always reach for state before I reach for I/O. If all I need to do is model some state, like manipulate some state, I will reach for that because that's the smallest thing that can manipulate state. But if I need to do other more like large stuff, I may still use state. I might use like state T of I/O, right? Because I don't want to mix my stateness and my I/O-ness. Because once you put things in I/O, it sort of is swallowed. Because I/O is everything. It's so big. Just pass it back to.
Hi, thanks for the talk. I have two questions, one specific and one much more general.
Okay.
So you talked about writing programs as being interpreting lots of little languages. And to use your coffee cup example up there, what I see is a list or a pair of two types.
Yeah.
Is that what you mean when you're talking about interpreting languages?
Do I mean?
Well, I would call that an interface with a tuple with two objects in it. And you just said in your talk that to get this functional approach, you need to sort of rejigger how I think, or my brain thinks as a programmer, into writing interpreters of data structures.
Yeah, so I think, so it's largely a euphemism, right? This whole idea about languages. What I'm trying to say really is that you can really think of any data type as a little language, and in the case of algebraic data types have associated algebras that sort of give semantics to those data types. And in the case of a pair, you can imagine how do you like handle a pair? You need a function that can receive both of those things. In the case of either, you need two functions, one that can receive the left and one that can receive the right. So it's largely sort of euphemistic, this idea of like a language, because all they are pure functions operating on immutable data types. So I could just say, instead of little languages, I could just say algebraic data types, and instead of interpreters, I could just say functions. Or algebras.
Okay, can I try another approach? Like, if you think about any problem you have to solve, it has some domain knowledge to it. So that domain knowledge is expressed in types, right? And interactions between those types, right? The types are the types, and the interactions are the functions, right? So what you call the language, like the language, is that kind of combination of types and functions in a domain-specific language. So in functional programming, you can write much easier this type of functions in
That's a good answer. I'm not going to repeat that.
So the second question then is, imagine that you're trying to go back and relearn functional programming from the start. Imagine that you have a good background as a professional programmer. Do you have any general advice on where to start, what to do next? Let's say I wanted to set a 3-month goal to get as far as I could in 3 months. What would I do?
Well, I don't have to imagine it. Like I was there. I was a professional programmer doing enterprise Java, and I came across functional programming. And I thought, wow, this is crazy. Why would anyone do this? But then, I started looking into it. But I think, the path for one person is not necessarily the best path for another person. And so,
Can I offer a suggestion, perhaps?
Okay.
I tried to come up with a bunch of refactorings for just general Java imperative code to try and make it more functional. And though I'm not going to say that list now, and I'm not even sure if it's completely correct, if you're programming in an object-oriented language, well, with Java specifically, try for a start replacing say collections with immutable collections, and Google Guava has a bunch of immutable collections, which are great. When you look at your code, you can understand a lot more easily what it cannot do, and also don't change the value of parameters, which most of the time you don't do anyway, and don't reassign local variables to new values, which I think people do in unit tests. And you'll probably see that you're starting to make that transition from imperative style code to functional style code, and then gradually you'll begin to see what makes something functional. That's my experience.
All right, yeah, that's good. I think that like the way that I learned functional programming was very sort of ad hoc. You know, like delve into Haskell and do some weekend projects and things like that, and mind bending at first. And just can't get your head around it. But so, you know, I wrote a book, Functional Programming in Scala, and it's intended really as a tutorial to sort of gradually go through. It's full of exercises. It's actually mainly exercises. And so, right in chapter 3, you know, it's about immutable data structures. So you start with that. Start with just using immutable data structures. It then goes on to handling errors using option and either. So instead of throwing exceptions, now you start using these things. And then this sort of gradually infects your code base. You start using state. And then there are some tutorials also on sort of designing libraries for doing other things. And you might get some ideas for libraries that you might design on your own. And in fact, we encourage that, you know, you take breaks in between chapters and just like experiment and just sort of make this a part of your work. Right? It's not so much about just like absorbing the information and like, okay, now I know this. Right? You have to practice it to make it part of your actual day-to-day work. You've had a question for a while.
So your book is a good resource for people who are engineers or software developers who have that experience but don't necessarily have the experience for functional programming, and they've already decided that functional programming is worth learning, or they're willing to give it a shot and they're willing to look through the book. But let's say you have the engineers who are very hardcore on the imperative style, and they go to a talk like this or they read a blog post, and you know, it doesn't necessarily click immediately, you know, how can we apply this to large production systems? Like, how can you have, like, it doesn't make sense how you can have a large system without using exceptions or without using state, or you look at a map and filter and it's like, this doesn't make as much sense as a for loop. What have you found are good ways for sort of convincing engineers with that mindset that functional programming is something that's worth looking at? Let's say you need to like convince a team or convince some peers that functional programming is worth looking at. Are there like particular like blog posts that you're aware of, or you know, talks that you really like, possibly like code bases that are complex enough that you could point someone at it and be like, you know, this is an example of a complex code base that uses all these things, but is also maybe simple enough that they could look at it and like look at what's going on and actually understand and see how these concepts are being applied.
Right. I think the answer to the last thing is probably going to be no. Because like the larger something is, the less easy it's going to be to understand for somebody who's just coming to it. Right? So it's sort of a necessary thing that people who are just seeing functional programming for the first time, all they're going to see are like simple examples, and think, oh, this is just for simple examples, right? I think that sort of goes hand in hand. But I really don't know the answer to your question, but I can give you some anecdotes. Like, I worked at a company called Capital IQ, and you know, it was a Java shop, and you know, I had a lot of developers. But my co-author, Paul, he wrote a subsystem if you rewrote it, so it was a subsystem that already existed using Java, and didn't perform very well. It was kind of difficult to maintain, and so he rewrote it in purely functional Scala, and it was awesome. Like factor 10 reduction in code base size. It was much faster because, and they used a lot less memory. So before it was all very sort of ad hoc, and you couldn't very well predict memory usage. But the way that he rewrote this was very sort of compositionally. So we could reason that we would always use constant memory in this particular subsystem. And I think that was very powerful for people to see that sort of success story. To see like an actual real world system implemented purely functionally. If you go and look at it, and the fact that it worked better and it was smaller and easier to think about, and then other developers who had never done very little Scala, they found it easy to maintain. Actually, I thought that was also a thought. So, yeah, I guess show them, and also I would just encourage people to try it. Like, try it on a weekend project. And if you don't like coding on the weekends, I don't know. How long are we going to do this?
The example that you just gave about your co-author rewrote the system and faster, is that because of the system could take advantage of multi-core because it's now pure and those kind of things, or even without concurrency it is faster just because somehow purity brings speed?
I didn't really catch your question. I'm sorry, you're asking about performance of what?
Yeah, so the example that you gave.
You mean just now?
Just now, yeah.
Okay.
Your co-author.
Yes.
The system, production system that you rewrote and that became faster, is that because of just purity or other benefits of purity like concurrency, because of that it's faster, or just alone,
So yeah, so why is it faster? It was mainly faster because the code is easier to reason about, and it's structured compositionally. So it's an analytics, it's a financial analytics system, right? And so it will do a number of calculations over large data sets. And what it was doing before was all kinds of sort of ad hoc transformations of the data set. And then in the purely functional version, what we were able to do is actually reason about whether we can do one sweep over the entire set. And then we use iterates and monoids and things to actually sort of accumulate partial answers. And yeah, we could actually take like 2 halves of the data set and accumulate in parallel 2 different things and make sure that we could combine the partial results. So it's not so much that the purely functional programs are faster. It's just that they're what you end up with is something that you can reason about, something that you can actually have some guarantees about how it's going to perform. And if you have self-similar components, then you can reason about the performance of the components, and you can reason about the performance of the composite. So it's just easier to optimize.
I have actually a question about kind of Haskell versus Scala. So you program in Scala, right? And Verizon apparently uses Scala.
Yes.
It's not written in Haskell. So it looks like in the end a little dirtiness is good, right? So the similar construction is OHML is used on Wall Street, James Street, right? But not Haskell. So I'm wondering, what is the evolutionary curve of this small movement, right? So if you gradually arrive from Java to Scala, does it mean that you will actually, take it to logical conclusion and will have to write in Haskell and Idris eventually? Or is Scala kind of a necessary and optimal maximal, right? Because the world is inherently dirty, we have to deal with these dirty systems, all the time. So we basically in your solution you postpone everything to the interpreter, which is the ideal situation, right? But in the real world, it's very rare that you have the final program, which is that interpreter and everything is pure. You actually have a lot of subsystems, and most of the time now you just have a lot of REST APIs, right, which basically you deal with. In each of them, you don't know the kernel. So I'm wondering if Scala found some kind of happy balance, right? Like, can you admit to some versions being good, or is it just kind of the best we got for now, and eventually we'll program in Haskell, but which is very fast and efficient and predictable?
I don't know. I think you're making a number of logical leaps. I don't think that that's that there's like a clear logical progression there. I think that no, there's no necessary sort of inherent like dirtiness. Like, we're not using Scala because we have to have some side effects. We're using Scala because we have to be on the JVM. So that's really the answer to that. And why are people using OCaml rather than Haskell? Well, because they like OCaml. OCaml is a lovely, beautiful language, and it's a pleasure to work in. So I can absolutely understand that people want to work in OCaml. So I don't think that there's any kind of like evolutionary progression that Scala is somehow a part of, and Haskell is the end game. I don't think that's true.
The reason people use OCaml more often is because there are many interactive programmers, so it's easier for them to use OCaml than Haskell. Other than that, I think Haskell is something
Thank you for your talk and your books. I appreciate both of them. Hey, I do have a question about the core architecture team. You mentioned that you basically the team polices itself for referential transfer security. And I was wondering about, you mentioned before, there's no nice static checks to ensure function purity. But I'm interested in the actual process that you use and sort of the heuristic to use. Like, one thing is like, look, if you're writing tests, if you have some complicated setup, it's a dead giveaway that, hey, there's some messiness. So I'm interested in how do you think about that, and what is your thought process?
That's a good question. Asked me to sort of introspect about that. I don't know that there's very much of an explicit thought process like that. It's largely just it's kind of like a silent agreement, right? We design the library, a given library, we design it from the outset to be purely functional, and to use, instead of throwing exceptions, we use some kind of error monad. Instead of actually going and perform I/O, we use like Scala Bay task or something like that. There are certainly cases, where I'll see somebody else has written some code, and I'll see that, they're actually like performing side effects, but in a way that may not be totally obvious, like they're inside tasks, but they're actually doing side effects. And we try to just kind of gradually get rid of that. But it's the process is just like a process of code review and an iteration.
Thank you.
All right.
In my opinion, that's the difference between pure programming like Haskell and Scala, right?
Yeah, that's the thing. If you're working in Haskell, you don't have to do this, right? I mean, you still have to do code review, obviously. But you don't have to look for this particular thing. You have to make sure that people are functional programming. Can't run on the JVM, but you may not have to.
Hi. Hey, I was wondering what you thought the functional programming differences were in Go versus Scala. High level, is one better to learn the concept in, or are there some things that just aren't maybe per se?
In Go versus Scala? I think that Scala is much better equipped for functional programming than Go is. And so I would definitely say that Scala is a better language for learning functional programming. Particularly things like higher kind of types and other things like that. I mean, there are things that you can do in Scala, and the things that Scala's type system helps you with. I think languages like Java don't do, languages like Go don't do. I haven't used Go at all. I've looked at its type system briefly. I would, from what I've seen, I would definitely say that Scala is more suitable for learning functional programming than Go is.
Cool. Thanks.
We are very close to the end of this meetup, so probably last question.
Okay.
So, if you have a large mishmash of existing Scala services and Java services and so on, you can, by selectively choosing to make some parts of it pure, you may be actively able to move the bottlenecks out. Do you see that? I mean, by moving all your I/O out, you can have the code that actually generates the I/O to be pretty much zero latency, and the interpreter is where all the latency is. Now, have you seen patterns where you can actually steer the latency and control the latency with this sort of selective purification?
That's a good question. I can't think of an example right now, but it's certainly the kind of thing that you can do, right? Because in the interpreter now you have a lot more information. There's a problem with like monads, for instance, because once you have like a function, if you have to call a function, there's nothing you can do to like manipulate the body of the function without calling it, right? So yeah, there's definitely some limitation there. But if you're using applicative functors or something, then yeah, I can definitely see that in the interpreter you can make a lot of decisions locally in the interpreter, but actually you're not making it globally over the whole program. And those decisions you would not be able to, those optimizations you would not be able to make if you in your individual calls. So yeah.
I think there's good motivation for making some parts pure.
Yeah, I mean in the credit card thing, I mean one optimization is that instead of calling the credit card, instead of charging the credit card n times, you could coalesce the charges. And you could say, okay, once per day, go and execute all of the charges and coalesce them with the same cards. Or if they're at the same credit card company, patch them up. Things like that. Okay, I think that's the end.